We are almost at the end of this course. We are just at lecture number 39. So, towards the end I thought we will study some of these modern control techniques, especially for the nonlinear control design philosophy. One of that happens to be integrator backstepping, and something on that we are going to study today actually. Towards the end of this lecture I will also talk about linear quadratic observer, which essentially leads towards Karmal filter and all that actually. These two are not related topics. I just put together because of time is sufficient to discuss both the things today actually. Alright, so philosophy of nonlinear control design using Lyapunov theory is something like this, because this backstepping design uses Lyapunov theory extensively. So, what is the generic philosophy? Suppose somebody wants to use Lyapunov theory for control design, then what is the idea there actually? Something is the idea is something like this. Let us say you have a nonlinear system, x dot is f of x u, where you want to design a control u in the state feedback form, which is like phi of x. So, u has to be as a function of x, phi of x, such that this once you put it back into the system dynamics, that is x dot is f of x and then phi of x, that system closed loop system dynamics would be asymptotically stable. That is the ultimate objective for Lyapunov based control theory actually. So, what is the idea there? I mean, how do you kind of make sure that that happens actually? Okay. So, the idea here is first you choose a positive definite function v 1, let us say, and make sure that v 1 dot is less than equal to negative of v 2, where v 2 is a positive definite function. And remember, these are all like sufficiency conditions and all that. So, you will not be operating in an optimal way, but you will be operating in on a conservative way basically, well, that is okay. So, what you essentially do is we select a Lyapunov function v 1 of x and make sure that v 1 dot of x, which is once you take v 1 dot, it is related to the system dynamics anyway. So, this v 1 dot of x would be less than equal to minus v 2 of x, where v 2 itself is a positive definite function. So, negative of v 2 is a negative definite function. So, you want to make sure that v 1 dot is less than equal to another negative definite function that way. So, that is the whole idea, design idea basically. So, let us see a small example before talking in lot more formal theory and things like that. So, this is a simple scalar problem where x dot is ax square minus x cube plus u, okay. And we want to design a state feedback control u, so that the closed loop system is asymptotically stable, that is the objective actually. So, we have to select a v 1 first. So, let us v 1 will naturally select a quadratic function half of x square. So, v 1 dot happens to be x times x dot, okay, obviously, because del v 1 by del x is x times x dot, and x dot is the system dynamics what you see here. So, we put it back here. So, essentially it leads to v 1 dot is something like this. Now, this v 1 dot has to be less than equal to negative of a positive definite function. Okay. So, we have to select another v 2 like that. So, let us say select v 2 is x square basically, let us say just I mean you can select any positive definite function for say, this is just one of those selections, and we want to make sure that this inequality is valid actually. Okay. So, v 1 dot is less than equal to negative of v 2. So, if you put v 1 dot is this expression. So, this expression is less than equal to negative of x square. So, then from there you want to solve for a controller, that means this x u is less than equal to this expression, and equal to sign will also is a valid thing. So, we will take equal to actually, and then make sure that u is equal to that. Okay. So, we cancel out x in both sides, one x will go from both sides, and then we have u is minus x plus x cube minus x square. So, is this control good or bad? I mean naturally it is good, because we have made sure that v 1 dot is negative definite function anyway, but still just to cross check about it, you just put it back this controller back into the system dynamics and then try to analyze what is going on there. So, if you put this system dynamics is x square minus x cube plus u. So, plus u whatever you are getting we will put it back. So, my x square minus x cube plus u is that portion actually. Right. This portion is like plus u. Okay. So, that is what you do, but then once you put it back these two are cancelled out, okay, and plus x cube minus x cube also cancels out, and you are left out with x dot is minus x actually. then x dot is minus x is certainly a linear system dynamics. So, actually and obviously because the eigenvalue is minus 1, obviously the system is asymptotically stable. In fact, it is globally asymptotically stable. Okay. So, that is because it is a linear system dynamics ultimately. So, it does not depend on initial condition, it is straight away from eigenvalues you can say it is globally asymptotically stable. So, that is the advantage here actually. So, you design a controller, it is a nonlinear controller in such a way that the closed loop system becomes globally asymptotically stable. But what is the problem with that? There is also a problem. Also remember that this V1 and V2 and Lyapunov theory, these are all like sufficiency conditions and all that. So, once you use that, the design can be actually conservative, and here it is actually a conservative design, primarily because this let us assume that okay, if you go back to this negative x q, x dot is minus x q is actually a stabilizing term, that is also like easy to see. For example, any odd power of like a scalar function, if I take any odd power of x is a stabilizing thing with a negative sign. For example, let us say x dot equal to minus x q, that one if you are talking, then corresponding to that let us say Lyapunov function, if you say just half x square, then v dot happens to be x dot, this is nothing but x times minus x q. So, it is negative of x fourth. So, it is actually a negative definite function. Okay. So, any odd power of x with a negative sign here will be actually a stabilizing term. Okay. So, but that what happens here is unnecessarily we have actually cancelled that out. So, this controller actually tries to cancel out the good part of it also basically. So, we do not want that normally. So, how do you avoid that? So, let us be because this is a small problem, we should be able to try analyze this a little bit more just by looking at the equations and all. So, let us see we select something like V2, I mean probably our V2 selection was wrong. So, we will revise this V2 selection and tell okay, let us consider V2 as x square plus x fourth instead. This is also a positive definite function by the way. Now, if you go back to this inequality again, that V1 dot is negative less than, I mean negative less than equal to negative of V2x, then the same analysis will tell that u is instead like that. And again you put it back and then plus minus x fourth and minus x fourth will get cancelled out from both sides, and you will be left out with that term actually. Okay. And here you will be able to, I mean cancel 1x and all that actually. Okay. So, anyway, so that is what will happen here actually. So, u will be like this. Again you go back and try to analyze what is the closed loop system. Then x dot is like this now, because that is my u. Okay. In this case this is my u now, okay, negative of u probably. Oh sorry, this is plus u. Okay. Okay. Okay, this is our system dynamics actually. So, we have to go back to this system dynamics and then tell this is plus u here. So, we put it this u, whatever u we are getting here, we will put it back and then try to see that x dot is instead minus a q minus x. So, we are able to preserve this beneficial nonlinearity, okay, by selecting a different V2. So, that is the message here. So, the design is not just unique design. So, it is subject to different selection of V2, V1 and all, you will end up with different controllers actually. But all of them will be able to do the job, and all of them will have some degree of robustness also, because these are all sufficiency conditions and all, robustness also comes into picture. Now, let us see how it is. So, suppose we go back to that initial selection, let us say V2 whatever we selected initially is x square. So, we will go back to that selection, and with that selection our closed loop system became something like x dot equal to minus x. But this x dot equal to minus x only if the parameter a is accurately known. Remember that this entire thing, this process of cancellation and all that, okay, what we did here, okay. Okay, this ax square and ax square, whatever this ax square and this ax square got cancelled out, assuming that the a is known perfectly. Okay, but if a is not known perfectly, then this a will be different from what is used in the controller, that a will be different, and hence you will not be able to cancel out. So, in that situation you will have additional term, okay, okay, subject to this. This is not no more x dot is minus x, it will be x dot equal to minus x plus an additional term with x square actually. Okay, so and plus x square is certainly a destabilizing term. I mean, depending on this how powerful is this a bar minus a is actually. Okay, that means how much inaccuracy is there. Now, no matter whatever is the inaccuracy, now because it is no more x dot is minus x, this suddenly this global stability is gone, and we can only conclude local stability, because globally this is no more valid actually. Okay, one is stabilizing term, other is destabilizing. So, obviously global thing is not there actually. However, if you make V2 sufficiently powerful, that means V2 is large and things like that, then obviously the control will also get more and more powerful basically. So, essentially what you are telling is, even in the presence of uncertainty like this, the design can be robust actually. Okay, because this term will not be that prominent at all actually. If your V2 is very powerful, then V1 dot is minus of V2x anyway. Okay. So, because that term being very high quantity and things like that, this will lead to robust control actually. So, that is the whole idea why this Lyapunov theory based controllers are typically robust actually. Okay. Alright, so with that much in the background, let us study about this integrator backstepping method, and then this is generalization of this concept what we just discussed actually. So, for here we need the system dynamics in a typical form, and for that form we let us start with a simplified form of that version, and this is the towards the end of this topic we will see this is like what is called strict feedback system and all that actually, but this is just one subset of that. So, what you are telling here is let x be n dimensional state, okay. Let xi be also a state, okay, where xi dot is simply u. Okay. So, x dot is f of x plus g of x times xi, and xi dot is simply u actually. Xi is a scalar, remember xi and u both are scalars actually. So, if the system dynamics is given in this form, okay, then I can think of using this backstepping idea and all that. So, remember that these both together are the state vectors actually, that means x and xi together will define the states of the system. Okay. So, obviously the states of the system will be n plus 1 actually. Okay. And where is this this pops up and things like that, probably if you see this any system dynamics in control affine form already, and you want to incorporate let us say actuator dynamics also, then this is the original control variable, but this part will be actuator dynamics. You want to see the total system that way, then it will pop up something like this actually. Okay. So, this is these are not very unrealistic problems in that sense basically. So, here we are talking about single input, and the control is scalar, and the xi state is also scalar anyway. So, that is the form that you are talking. So, what are the assumptions? Assumption is first is f and g are both smooth, okay. That means the derivatives are also continuous. F of 0 is 0, whatever the f of 0 you are talking here is should be 0, and if you consider this xi as a control input to this particular state, the first part of the equation xi acts as a control variable. So, if you consider that, okay, then we assume that there exists a feedback controller already in the form of xi equal to phi of x, where phi of 0 is 0. Okay. So, that means assuming this is a control variable, we have already designed a controller in appropriately. So what does that mean? Xi is already designed as a function of x, where phi of 0 is 0. Okay. Because it is a stabilizing controller, it also has a Lyapunov function with that. Okay. So, there exists a Lyapunov function V1, such that V1 dot, which happens to be like this, like del V by del V1 by del x into x dot. So, x dot is like that anyway, right. So, that is less than equal to certain negative of Va of x, okay, where Va is a positive definite function. That means, all that you are telling is first part let us consider is as a separate problem, okay, for which xi is a control variable, and that this xi is actually already designed as a state feedback form with all good behavior basically. Okay. So, but in a given problem we need to design this xi also basically that way. Okay. And as I told, this backstepping design is kind of very popular for incorporating actual dynamics into the system and all that actually. So, anyway, so this is the assumption here. Now, what we want to do? Now, we want to design a u, okay, you can think of that as input to the actuator probably, so that the overall system remains stable actually. Okay. So, that is the problem here actually. Okay. So, let us see how do you do that. But observation, let us say one important observation before you move further. let us consider what happens when x is already equal to 0, x has gone to, let us say x equal to 0 has already achieved, okay, then what happens. Now remember phi of x by definition phi of 0 is 0 anyway, okay. That is how this xi is already designed. So when x equal to 0, then phi of 0 is 0, that means xi is also 0, okay. So this part is 0 anyway, okay, and then f of 0 is 0 by assumption, okay. So x dot becomes 0, so no, right. So when x goes to 0, x dot is already 0, so that is fine actually. So the system will go to equilibrium condition and it will stay there, so that's more important actually. So that is not a problem. But then the problem happens in the other way around, like what happens, okay, when x goes to 0, nothing, not a big problem actually, but what if this xi goes to 0, okay. When xi goes to 0, this system dynamics, the first part of the system dynamics is almost become some homogeneous dynamics actually, okay. Xi can go to 0, so this part is not there, but x dot is f of x, that system has no guarantee then that x will go to 0, that system dynamics is homogeneous dynamics. I mean only in the closed loop sense x will go to 0, that is how the guarantee is already there, that is we have already designed a feedback control of for that behavior, but for the homogeneous system there is no guarantee actually. That means when xi goes to 0, we are not very sure that whether x will go to 0 or not actually, but that is not allowed actually, because our total aim, the final aim is to make sure that x goes to 0 also basically. So how do you do that, okay. So that is the core problem actually, okay. So for that we need to do some algebraic manipulation as follows, okay. So let us see what we do there. So for this particular system dynamics, the first part of it contain only this part f of x plus g of x times xi. So now let us add and subtract these two terms actually. So this will add g of x times phi of x and subtract g of x times phi of x, okay. When you do this operation, okay, let's consider this part of it, will keep it, okay. Remember this phi of x is the same phi of x that we are talking actually here, xi is already designed in the form of phi of x actually. So it is just an algebraic manipulation sort of actually, okay. So what you are doing here, so we are keeping this part of it here, and then this part and that part will combine, okay, and then tell, okay, this is what will happen actually. So g of x times phi of x plus g of x times zeta minus phi of x. Obviously we are not changing anything here, I mean the system dynamics, we are just I mean playing around with a little algebra actually, without altering the system dynamics. Now with this change of, now this xi minus phi of x, let me define it something like a new variable z actually, okay. So I am just defining that for math simplicity sort of thing. Once I do this definition z, then the system dynamics is nothing but that f of x plus g of x times phi of x plus g of x times z actually. Now what actually, earlier when zeta goes to, I mean this xi went to 0, then we had a problem, but what if the same problem is there or not, okay. When you see this system dynamics in this way, that means when z goes to 0, this system is no more like only f of x, this system is f of x plus g of x times phi of x, and phi of x is designed appropriately already basically. That means when z goes to 0, this system dynamics is no more a purely open loop system dynamics, it is actually a closed loop system dynamics, and hence this is asymptotically stable anyway. So x will go to 0. So the problem that we had, that when xi goes to 0, x will need not go to 0 in general, that does not happen when z goes to 0. When z goes to 0, x is bound to, I mean supposed to go to 0 basically. So that problem will be overcome that way basically. Now how do you do further algebra, because we have to put it into this form, that form has to be there actually anyway. So let us analyze this z actually. Z is by definition xi minus phi of x. So we put it, z dot is xi dot minus phi dot. So we put xi dot is nothing but u, okay. So this z dot is nothing but u minus phi dot actually, okay. So we have this system dynamics, like this modified system dynamics in this form, okay, where z dot is nothing but v is this artificial control variable that I am interpreting, that u minus phi dot I am defining as v and interpreting that, okay, z dot is nothing but v actually. So if you see this system dynamics, okay, now it appears in the similar form that we started with actually, okay. So this form is nothing but something plus g of x times z, and then the next one is z dot is v. So this system is equivalent to the original system actually, Okay. So, only problem is instead of I mean this phi is used in the form of phi dot actually. Okay. So, and phi dot can be computable, and that means del phi by del x into x dot, and x dot is available anyway. So, that is the way you compute phi dot. So, what is going on in a block diagram sense? This is the original system dynamics, what we started with u and then integrate it goes to see if you see this u, if you integrate it is zeta, sorry xi. So, that is what it happens here. Okay. If I have u integrate, you will get xi, then it multiplied by g of x, I get g of x times xi, and then this feedback operates that way actually. Okay. So, what you see here is f of x plus g of x times xi. Okay. So, that is x dot. Okay. So, that is how it happens, but what you are doing here is first of all we are putting a g times phi here in this loop, and for that reason we have to introduce a negative phi of x here. But we do not stop here, this phi of x is really not introduced here, it is introduced one block before that, and because of that we have to introduce phi dot instead, negative of phi dot. Instead of phi of x, it is introduced as negative of phi dot x actually. So, phi to phi dot is actually backwards actually. So, whatever is integrated that signal flows forward, whatever is differentiated that signal flows backward. That is why it is called back stepping actually. So, you are just stepping back in the block diagram one time, and then interpreting that u minus phi dot sort of thing because of this algebra basically. Okay. Okay, this entire thing is borrowed from this book, and if anybody interested, they can see this book also. This is a good book, I think. All right. So, this integrator backstepping. Now we have to see that how do you design this v of x and things like that. Now we are talking about this system dynamics. Remember that. So, how do you do that? So, let us start with this v of x. Now we have to define a Lyapunov function inclusive of z. Okay. So, we will define something like v1 of x plus half z square sort of thing. So, v dot is nothing but del v1 by del x times x dot, and x dot is all that, because x dot is what we derived actually. So, the entire expression will put it back, and once you put the entire expression this plus this z times z dot. So, this term will give us z times z dot, and z dot is nothing but v. Okay. So, this z dot is v, that is what we will put here actually. Okay. So, that is how we will end up here, and so but this part of the system, this part of the algebra is nothing but negative of v of x. That is what it is, we are assuming that is already designed that way. So, this is available to us actually, right. By the way we started that okay, this I is already designed with a associated Lyapunov function which satisfies this inequality. So, V A is available to us. So, we use that. Okay. So, this is nothing but less than equal to V A of x. So, we keep this part is less than equal to V A of x. Now, if you see this part, this one and that one together sort of thing, and that is what we will combine actually. Okay. So, then once you combine these two parts, okay, this first part and this term, and then you have as z times v actually. Okay. So, when you combine these two terms, we will end up with this negative v of x here, that is already available to us anyway, plus this additional term actually. Remember, z is common to both actually. So, I can take out z actually. Okay. So, that is what happens here. Now, the question here is how do you make sure, how do you design a v such that this entire thing is negative definite, that is the whole point actually. So, when you see something like this, the very natural idea that comes to mind is okay, let me design a v this way. So, I will cancel out this term, and whatever is left out it will generate something like a negative k times z square, where k is positive. So, naturally I will select a v which negative of this quantity, okay, minus kz, so that when minus kz is left out here, it will generate a minus kz square term actually. Okay. So, that is the whole idea. So, now v dot turns out to be less than equal to a negative definite function that is already available minus kz square, okay, which is also negative kind of semi definite and all that actually. Okay. Because if you see the total okay, So if you see the total things like total system dynamics, the entire Lyapunov function must contain both x as well as z actually, right. Then only the system dynamics we can conclude something actually, okay. Because any part is left out, we will have a negative semi definite sort of idea there. So when you see this entire function, the first part assures that it is negative definite for the first part of the system dynamics, okay, and the second part will assure that it is also negative kind of semi definite for the second part. So combinedly together sort of thing, they will have a negative definite function for the bigger system, total system actually. So that is the way it will have a negative definiteness actually, okay. Alright. So whole idea, what is that actually? Now the whole idea is V turns out to be like this, and V is also known to us already. V by definition is u minus phi dot, and phi dot is anyway available. So using all that, I will be able to extract a u basically, okay. So V is already u minus phi dot. So I will, and phi dot mean that expression is available to us anyway, because V is designed like that. So that is equal to that, and phi dot is anyway there. So u equal to phi dot minus that, and phi dot is like this already there actually. So that is how we design the control u basically, okay. So but also note that in this entire exercise, first one should design this phi of x, because without that it will not proceed further, but that is anyway there actually for this method to start. The phi of x should be designed actually first, okay. This what you are assuming here, that there exists a feedback law for xi equal to phi of x with phi of 0 0. So that has to be designed first, okay. Then you design this u and all that. So let us see a simple example again, like x1 dot is the same example. Probably what you go back, instead of u we will put x2, and then x2 dot equal to u. That is how we will make it a second order system, so that it is compatible with the theory that we discussed. So ultimate objective here is u has to be designed, so that overall system becomes asymptotically stable. Now we have already designed x2 before, and let us repeat that exercise one more time. So we will tell, okay, you will consider x2 as a control variable for the first equation, and then will I mean either you go ahead and put this entire like we identify which one is what and just plug into the formula and get the answer, or you can start from the beginning and get the answer either actually. So you have this v1 of x is like that. First of all, you have to find a phi. For finding that, you will take v1 as half x1 square. Now v1 dot is like that, and it should be less than equal to some va of x1. And following that previous example that we started with, the same example, we will take x1 square plus x1 fourth, which will not cancel out the good nonlinearity part of it. So we will keep it that way, and hence we will cancel out all the thing and design this x2, which is earlier we designed it as a u, but this time it is x2 basically. So this turns out to be phi of x1. So that is how we got phi of x1 actually. Now we will go back and modified system dynamics we have to write. So we will add and subtract and things like that. So we will write this x1 dot in this form, and where this z dot is v and v is defined as u minus phi dot. So that way we will define actually, okay. So we have to take this v as v1 of x1 plus half z square again, that is following the same theory that we just discussed actually, okay, here. So we will put that the same idea back in here, tell, okay, v is v1 of x1 plus half z square. So v dot is nothing but v1 dot plus z times v, z times z dot is v anyway. So that is what it is. This entire algebra gives us like this, and then we will tell, okay, this v has to be, when this algebra whatever you see here, v has to be minus del v1 by del x1 minus kz square, okay. So that I mean minus kz basically. So that is what it is. So if you put it back and try to solve for your control, so v is nothing but u minus phi dot. So u equal to phi dot minus x1 minus k, but phi dot is nothing but del phi by del x1 into x1 dot. X1 dot is like that, minus x1, so minus x1 minus k times that, so minus k times that, okay. Phi of x1 is that way anyway. So you now you expand all the things algebra and then get a controller of that form actually, okay. So this k becomes a gain value, which is positive number, which needs to be tuned for your good performance basically. So that is that's how an example actually, okay. So what is the associated Lyapunov function for this? The composite Lyapunov function turns out to be v1 plus half z square. So v1 is obviously already there, and z square is nothing but z is by definition okay, u minus phi dot sort of thing, right? No, that is z dot, sorry. Okay. So, z is nothing but this what is that the definition, so okay, this one x2 minus phi of x1, so that is that's z. So, we put x2 minus phi of x1, so that's that part of it. So, this is the composite Lyapunov function for the total system actually. Okay, first part is only for the first equation, when you put the second one it becomes the Lyapunov function for the total system actually. Now, more general case, so this is all about like we have this type of system dynamics to we started with. Okay, this is the foundation stone anyway. So, we started with where x is n dimensional state and one more state is there z dot and that is equal to u. So, that's how we started with. What about more general case actually? So, when you take more general case and all, so this all happens to be not that difficult at all. So, you take okay, this let us consider this one as a natural extension actually. We have xi1 here where xi1 dot is i2 and then xi2 dot is u. Okay. So, obviously, the idea is successive iteration actually. Like if you consider only this system first, the first two equations first, once you are done with that you will get as i2 and then you consider okay, this first subsystem is 1 and then you add one more xi2 dot is u. Okay. So, successively you have to design 2 times actually. Okay. And this if is the system dynamics is analogous, that means let us say the system sequence does not stop here, but it is like xi2 dot is xi3, xi3 dot is i4 and xi4 dot is i5 like that, and then somewhere let us say xi10 dot is u like that. So, you have to repeat the exercise like 10 times actually. Alright, so we concentrate only on this. Okay. So, where we talk about this xi2 dot is u and then let us see what happens actually. So, first we will consider only the first two equations. Okay. For the first two equations we have just done everything. This first is like xi1 and for that xi1 phi of is like exists already and we have to design something like xi2 considering these two equations together. So, we will proceed the exactly same thing that we just discussed and we will tell okay, this v1 the corresponding Lyapunov function is available, xi1 can be done the way we just discussed actually. So, then we will take okay, by the time by the way that we just so this part of it. Okay. So, we just do that. So, the analogous the inference is we can directly write xi2 instead of worrying about all the derivation one more time. So, let us write xi2 and xi2 has to be in this form, okay, del phi by del x into x dot minus this term minus that term and all that actually. Okay. So, that is available and also have a composite Lyapunov function for this system which is like v1 plus this one, that also we just discussed. Now, what about extending to one more actually? So, if you want to extend this step, this is about step 1 sort of thing, okay, that we just derived. Now, about step 2 we have to consider this one more state into the picture basically. So, we will tell okay, this state is first state is like that, first subsystem is like this and then we are adding one more xi2 dot equal to u. Okay. So, you consider this part of it is something like f1 of x1 where x1 is xn zeta 1 so xi1 together and then tell okay, there is a xi2 term here. So, I will put it there that way actually. Okay. So, x1 dot is this expression. So, f1 of x1 plus g1 of x1 times xi2. So, x1 by definition is like that. So, this expression what is here, the first part of it I will just change it, the definition is x1 instead of x. So, it is x1 dot is whatever is there in the first equation, then xi2 dot is u. So, then again we know how to do it. So, we will do this algebra again and then tell okay, u now becomes like that actually. Okay. So, entire big expression what we operated here instead of x we will have to operate it based on x1 dynamics actually, and v is to be v2 plus xi2 minus phi 1 of x1. Okay. So, that has to be carefully noted actually. Okay. And this phi 1 happens to be all that by the way, this entire thing is phi 1. Okay. So, longhand algebra is a necessity in this approach anyway. So, you have to have you should not get impatient with this algebra and all that, but essentially it is lot more bookkeeping rather than too much difficulty actually. if you once you understand the one or two steps, then it is just extensions of that same idea basically. So, we have this and then put it back here and then tell okay, using the same idea we will get a u, and the composite Lyapunov function for the entire system, that means this system together, okay, x dot xi 1 dot and xi 2 dot happens to be like that. And as I told before, this is actually not very unrealistic, because if you see this xi 1 as control, okay, to the original plant, but this is like a second order actuator dynamics. Okay. First order actuator dynamics is what we thought, I mean we just discussed in this first part of the thing. We have a first order actuator dynamics, that will happen that way. If you have a second order actuator dynamics, that will I mean the two equations, that will happen that way actually. So, this will be augmented to the system dynamics. You want to design a robust actuator input and all that. So, then this is the procedure, one of the procedures that is available to you is backstepping actually. Okay, so, we will go there and then this is about that, and then we talk about okay, what is the best generalization that you can have this approach actually. The best generalization turns out to be in the strict feedback systems, and all those things that we discussed are subsets of that anyway. So, strict feedback system is something like this, you have x dot is like that, zeta 1 I mean sorry xi 1 dot is like this, where xi 2 is an input, xi 2 dot is like this, where xi 3 is an input, like that it will continue to some arbitrary order k basically. So, if it happens like that and there is a very strong assumption here by the way, what it tells you is all these functions that you are looking at, not the first one, but starting from g1, g2 up to gk, all these functions are certainly not equal to 0 over the entire domain of interest for all time. That is actually a very strong assumption, but with that assumption we should be able to solve it actually. Okay. So, what is the whole idea here? I mean, we will not worry so much about this functional dependency and all. Let us consider only this first two terms sort of thing. Then this whatever is appearing here f1 plus g1 times i2, I will simply define it as something like a new variable sort of thing. So, let us consider only that part of it. So, x dot is f plus z times I, where z dot is f a plus z a times u. Okay, so, that way. Then what you are defining is this I dot is V, and you carry out all the algebra, because once the I dot is V we know how to do it, and ultimately once we are done with V, you can extract U from that actually, because this is by definition V. So, this is equal to V. So, then if I solve it for U, this is simply an algebraic equation anyway. So, I will simply go ahead and solve for U basically. Once I solve for U, this is the expression that I will end up with actually. And I can do that because by assumption G A is not equal to 0 anyway. Okay. So, that is anyway there actually. Okay. So, with that I think we will I thought this topic I given sufficient exposure for anybody to work with these backstepping ideas and all that. So, you can see one of the ideas that we use for this analysis tool, which is Lyapunov theory. Before we have seen how it is useful for neo-adaptive design. Now, this class we have seen how it is useful in backstepping design directly actually. And various ideas do pop up in the literature, where you can think of let us say use that in an observer setting also, like how do you design observers based on Lyapunov theory. Okay. So, it is a very generic tool where you can think of exploiting that for design purpose as well actually. Okay. So, with that exposure I think I will proceed to a different topic now, and then the rest of the time we will talk about that actually. Alright. So, this topic is the linear quadratic observer. Okay. So, this is what you have seen before in that some time back is this pole placement type of observer, where this was valid for single input system and all. The moment it was multiple input and all, there is a lot of ambiguity, confusion and all that. How do you do that? And there are suggestions and all that, but then it is not very unique way of doing things. So, this particular observer design is is not restricted to that. In other words, you can have multiple input system for the control design, and hence for the dual system you have multiple outputs also. So, the pole placement type of observer is valid for only single output system, whereas this LQ observer is valid for multiple output system directly basically. So, you can have number of measurements many basically, That is the advantage that you talk about LQ observer. Second bigger advantage is this gives us a platform to develop towards Kalman filter, which is even more elegant actually. Okay. Having said that, you can also note that this LQ observer is actually nothing but a Kalman filter. So, a special Kalman filter sort of thing you can think about, and then hence even if you have this noise input in the system, then also it is capable of filtering it out actually. Okay. So, we will see that little bit glimpse of that, because I thought without this exposure of LQ observer and little bit of Kalman filter at least, no control theory course is complete actually, because most of the time we have to use some form of observer or filter like that actually. So, let us see what is going on here. So, why observers? We have seen this before, that the state feedback control designs need the state information for control computation, and in practice all states may not be available, and possible reasons can include let us say sensors are not available, sensors can be very expensive, and quality of the sensors may not be acceptable due to the noise content in that also. So, you probably do, if you are given a choice, you will not want to use that sensor actually. So, what is an alternative? Let us say we use limited sensors which are of good quality anyway, and then rest of the states we want to kind of have an estimate of that based on those measurements in a sequential manner actually. I mean, you will take measurements multiple times, and from them from that information we want to observe, or we want to estimate what should be my state and things like that actually. So, what is an observer? An observer is nothing but a dynamic system whose output, or output of the observer is an estimate of the state vector itself actually. Okay. So, that is what you are primarily bothered about, estimate of the state vector x. Obviously, observer can be a full order, reduced order, things like that. These are topics of further discussion and things like that. We will not talk about that, we will simply confine ourselves to full order observer even in this class actually. Okay. Now, also remember that before talking an observer, the observability condition is a must actually, and it is also true for filter designs as well. If the system is not having observability property, then we cannot design an observer really. Okay. So, that means we really need additional sensors, some information that we cannot capture using limited sensors and all that actually. Alright. So, observability condition must be there, and we are interested in full order observer, and we are interested in linear quadratic observers. That is the objective here actually. So, let us see what is what we are interested in here. So, let us plant is x dot is x plus b. All that I am talking about is linear systems again actually. So, we talk x dot is ax plus bu and y equal to cx. Okay. So, this is nothing but the sensor output vector. So, sensor, whatever sensors you are getting, that you are writing is as a linear equation y equal to cx, and let the observed state be xit in the observer dynamics. Okay. That is what we want to have an estimate. So, that is that let denote that as xit, and xit dot is nothing but that actually. That is almost same thing as that x plus bu plus key, but this plus key is an additional term that we are interested to put in there. So, that is how we will inject sensor information into the dynamics actually. So, what is our objective? Xit should go to x as soon as possible. So, when I define this error x tilde is x minus xit, that means x tilde should go to 0 basically. Okay. That is the thing, and remember when you are talking about observer, we are not talking about any noise in the system. So, neither process noise is there in the system dynamics nor sensor noise is there. Okay. So, in that setting we are just talking that only we are telling that all states are not available from the sensors. From that we will try to estimate something actually. So, when you define error like that, so obviously the error dynamics is also associated with that. So, x tilde dot is x dot minus xit dot, so x dot is x plus bu, xit dot is that, we just put it there, and then do this simplified algebra. So, you can do this add and subtract this a tilde x and things like that, you will end up with something like this. Okay. Now, we have something, when you have something like this, obviously we do not want to see, given a choice, if it is possible, we do not want to see this error dynamics as a function of original state and original control. So, you want to see the error dynamics as a function of error itself primarily. So, if you can do that, that is the best actually, and because these coefficients are available, probably we can do that actually, because we have never selected what is so far you have not told what is a hat and what is b hat. So, this will actually give us a platform to actually tell what is A hat and what is B hat, because we will make sure that the coefficients go to 0, that we will get B equal to B hat and A hat equal to A minus K E C. But as a byproduct of that, as a good byproduct in fact, the objective of what we wanted, that means that the error dynamics is a function of error itself, is happening actually. So, it is now decoupled from x and u, because x can be large and x tilde can be small. Similarly, u can be large, x tilde can be small. There will be lot of numerical compatibility issues and all that will be avoided actually. So, by doing that, so what I am telling, these coefficients have to be 0. So, once you have these coefficients 0, this results in A hat is nothing but A minus K E C, that is what it is, and B hat is nothing but B. Okay. So, once you have this, then you go back to this system this observer dynamics and tell, okay, now A hat is nothing but A minus K E C and B hat is B. So, let me put it back, and then once I put it back, I get something like this. Right. So, x hat dot is A x hat plus B u plus K E times y minus C x hat, and this y is your actual like sensor output, and C x hat is estimated sensor output. That means y minus C x hat is also called innovation, residual and things like that actually. So, this is y minus C x hat is that part of it is called typically it is called innovation actually, okay, in the filtering setup. But that is the extra error information that you are giving to the filter dynamics or the observer dynamics to get it get some better estimate of the state basically. Right. So, what is your what is our interest here? Now, if you go back to the error dynamics part of it, our objective was this should go to 0, right. I mean, that is the primary objective. This should go to 0 as soon as possible. That means, if I see this residual error dynamics, then that error dynamics would be asymptotically stable actually. Okay. So, that is what I will do here and tell, okay, what is my residual error dynamics? This x tilde dot is now A hat x hat, remember that is only this part is left out, and A hat is nothing but A minus K E C. So, what I am left out with A minus K E C actually. So, that is my error dynamics. Okay. Now, let us go back and see what is what we have done in the LQ control design, that is linear quadratic control design using LQR theory and all that. There, if you have designed a controller in such a way that the closed loop system dynamics happen to be like this x dot equal to A minus B k times x, and here it is the closed loop system dynamics error dynamics in fact, which is like x tilde dot equal to A minus K E C times x tilde. Here the objective was to make sure that x goes to 0 as t goes to infinity. Here also the same objective, x tilde goes to 0 as t goes to infinity. So, almost very parallel to what you have seen there actually. Okay. But the only difference is this k appears to be in the right hand side here, but where this k e appears to be left hand side here actually. Okay. K e stands for let us say estimated gain actually, I mean gain of the estimator basically. Okay. So, to avoid this problem, what we note is that, okay, in this particular matrix, all that we want is this is Hurwitz, that means the eigenvalue of this matrix has to be all in the left hand side. And this is, if I really am interested in only in the eigenvalues, then I can very well visualize the transpose of this matrix as well. Now, if I visualize the transpose of this matrix is nothing but A transpose minus this transpose will now change this order. So, it will have C transpose K E transpose. So, what appeared what happens, I mean what appears in the left hand side now appears in the right hand side, and hence the problem is compatible, provided we interpret this A as A transpose here and this B happens to be C transpose. So, A is equivalent to A transpose, B is equivalent to C transpose, then K E transpose is something that is equivalent to our kind of controller gain actually. So, this is anyway that is compatible with what we call as dual systems and all. We have all discussed about this dual system dynamics when we are discussing about controllability, observability and observer and all that actually there. Those of you have forgotten, you can revise those lectures to see what were those actually. Okay. So, this is the observation. So, in control design we have come up with something like a closed loop system dynamics like this, objective was like that. Observer design that we are talking here is the closed loop system dynamics is like this, objective is also like that. To make sure that the gain appears in the right hand side, visualize the transpose problem, and the transpose problem happens to be like that actually. So, now we go back and see something like this dual system idea that I just talked about. So, we talk, okay, as a summary something like the system is original system is like this, the dual system that we visualize is something like that. Now, if you see the controllability matrix and observability matrix here and similar things here, then the controllability matrix turns out to be observability matrix here and vice versa, observability matrix here turns out to be controllability matrix. Okay. So, instead of designing like another observer or something, what you really do is we design a controller for the dual system actually, and that will become an observer for the actual system. Anyway, so the LQR design we already know how to do it, u equal to minus kx. So, using this philosophy we will be able to directly derive a gain for the filter, I mean the for the observer. So, let us go back to that. So, this is the closed loop system dynamics, and this gain that we are talking here was designed as something like R inverse B transpose P, where P is a positive definite matrix which comes out as a, I mean which is found from the solution of the algebraic Riccati equation. Okay. So, this Riccati equation like that. Similarly, analogous system we see here, this is like transpose and all, this acts like a controller gain as I told, and this controller gain can be directly written as something like this. Remember, R inverse B transpose is equivalent to like B transpose equivalent to C. So, we will put C and this P is P, but the P is the solution of observer Riccati equation, not the controller Riccati equation basically. Okay. So, you see that an equivalent system, whatever A transpose, C transpose, B transpose that we have, we can plug in back here and then tell okay, this is what should happen actually. So, this type of I mean this equation is called I mean filter Riccati equation or observer Riccati equation either way. So, you get a solution of this system dynamics, okay, sorry this Riccati equation, and then whatever solution you get, you put it back, that will become your Ke transpose, it is no more Ke, but if you take the transpose of that, you get Ke basically. Once you get Ke, this is your observer dynamics. So, this observer dynamics can be propagated, and as you propagate it will ensure that x tilde goes to 0, and hence x hat will go to x actually. So, that is how it operates actually. So, this is that algebraic Riccati equation based observer design. So, it is nothing but LQ observer design, linear quadratic theory is coming into picture basically. And this particular idea that we just discussed can be extended to this Kalman filter design in the linear time invariant system case, in the continuous time case actually. So, very quickly we will see some a summary sort of thing here. What it tells is okay, system dynamics is something like this. Now, it is Ax plus Bu plus GW, and Y is nothing but Cx plus V, and this W and V are process, I mean W is process noise and V is sensor noise, and they are vectors in general and things like that, and there are bunch of assumptions here which tells that okay, this first of all this W and V has to be like 0 mean, the first is 0, that means 0 mean, and then they have to be like mutually orthogonal, they have to be white noise and things like that. W and V are uncorrelated white noise actually. Okay. They are not correlated to each other, and they are like white noise definition, if you see, they are I mean this I mean there is something called this whiteness property and all that, they have to be satisfied. I will not talk too much detail in this lecture, but just remember that they have to be like white noise actually. Okay. And then it also talks about, like when I talk about W transpose and then take expected value, it will have only Q there. Remember, this is a little bit translated in the time actually. So, if I take only the same time, I will get some value. If I have any difference in time, that will not, that will be 0 actually. So, delta definition is like that. So, similarly for V also there actually. Okay. So, all these definitions intact, all these assumptions, I mean with all these assumptions, we are still putting the objective that okay, let us estimate x hat, so that the error goes to 0 actually as t goes to infinity. Now, can we do that? So, the entire derivation I will not do it anything out of that here, but let us see in the summary sense, this is something very parallel to what we have done before. We will still take an estimator dynamics, okay, and here with this Ke is called Kalman gain actually, or estimator gain or filter gain, whatever you can talk about, exactly same as what we discussed in the observer actually. Whatever observer equation is there, it is same as that actually. By the way, this is x hat actually, x hat. Okay. So, that is exactly same as what we have discussed actually. Okay. Now you tell okay this x hat is E expected. Now x hat what you are talking actually not directly the same state or something. Now it will have estimate of the state itself what you call as expected value of x. Expected value is like an average value for many measurements, I mean many cases and all. If you take lot of this values and all, then take average and average value, then that is nothing but expected value. So, all the thing that we are discussing here is in the estimated value sense, sorry expected value sense, that means the average value sense basically. Then similarly the y hat will be expected value of y, and then when you put y is nothing but Cx plus p, and then you assume the expected value is a linear operator. So, you can separate it out and then C will come out, and then this is 0 by definition, the expected value, this is 0 mean actually, both W and V are 0 mean. So, that will make sure that expected value of V is 0. So, you will end up with y hat is nothing but Cx hat actually. Okay. So, whatever y hat we are talking here, nothing but Cx hat. Okay. So, very similar to what we have done before. So, only difference is this x hat is expected value of state now, is no more a deterministic value. So, the question here is we know the system, I mean the filter dynamics. Now, how do you design this KE? And that part I will not talk anything here, but the summary turns out to be like that. You design KE exactly like what you have done before, but this P, that the Riccati matrix will be a solution of that. Okay. And if you see this the only difference that we see here compared to this this equation is, if you see this equation and this equation, okay, the only difference is this part actually. So, earlier there was no G here and G transpose there, now it has actually. So, if you assume that this system dynamics has G as identity, okay, then that is nothing but the LQ observer is nothing but the Kalman filter with the assumption that G is identity. Okay. So, that is that's how it operates. So, what's the thing here? So, we have a filter dynamics like this which we need to propagate. So, we initialize something and start propagating, but we need a gain value here Ke. So, Ke can be computed that way, but in this expression we need a P. So, P can be computed from this equation. So, you have to implement it, then implementation sense has to be something like this. You first initialize x at 0, then solve for this P matrix from this Riccati equation. Once you get a P matrix, you compute the gain, filter gain. Once you get the gain, you know the filter dynamics anyway. The filter dynamics and your initial condition is available. So, simply propagate this equation forward in time actually, and it will all make sure that your error goes to 0 in an expected value sense actually now. So, your mean will go to 0 and then you will get a, I mean your noise will get filtered out and things like that actually. Okay. So, this is all happening in the, this all happens in the continuous time linear time invariant system Kalman filter theory. It has gone much more beyond that. We talk about discrete time implementation, then continuous time system propagation and discrete time measurement implementation. This continuous discrete version. Then there are extensions to make it operate for the nonlinear system, that is extended Kalman filter and things like that actually. So, these are all available. So, but also remember that without knowing this some of these estimation theory, the control design is perhaps slightly kind of incomplete actually. So, I will encourage all of you to study further in this field and then get comfortable with all that actually. So, with that I will stop this lecture. Thank you.